So for question 115, for exercise 115, it's important to understand a concept that will be carried through all of Organic Chemistry 1 and Organic Chemistry 2. It'll be a principle that explains so much, and it's called electronegativity. Electronegativity is how attractive a nucleus is, or how much a nucleus attracts valence electrons. So you know the nucleus has all those protons in them. So those have a positive charge. They're going to attract electrons. Electrons wrap around the nucleus in layers. The outermost layer is the valence layer. So how much does a nucleus attract those outermost electrons? And those are the electrons, valence electrons, are the electrons in bonds. So the electronegativity tells you how much an atom, a nucleus, is attracting the electrons in a bond. Now the trend for electronegativity is that it increases as you go up on the periodic table and as you go to the right, it increases. So the top right of the periodic table is really the most electronegative place. The reason why it increases as you go up is that we're talking about valence electrons, and as you go up, there are fewer, as you go up, the electrons get closer to the nucleus. So here at the top, they'd be really close, and as you go down, the electrons get in more and more layers, and they get further from the nucleus, so they don't feel it quite as much. So the electronegativity increases as you go up, because the electrons get closer to the nucleus, so they can feel that positive charge more. And the electronegativity increases as you go to the right, because as you go to the right, every time you move over from one element to another, you, in the same row, you add a proton. So hydrogen has one proton. If you go to the right, helium has two. And so now that's more positive charge. Two protons, that's more positive charge than one. And so that positive charge attracts our electrons more. So electronegativity increases as you go up and to the right. So what happens if you have a bond between between atoms that have really different electronegativity? For example, oxygen is way up here at the top right of the periodic table, and hydrogen is way over on the left. So oxygen is more electronegative. It attracts these electrons more than the hydrogen does. That means that the electrons are going to spend more time around the oxygen, and the oxygen will become slightly negative. The electrons are going toward the oxygen, they bring their charge, their negative charge with them, and so the oxygen becomes slightly negative. And if they're going toward the oxygen, they're going away from the hydrogen, so the hydrogen is left with a slightly positive charge. It doesn't have as many electrons as it would if it were neutral, because the electrons are leaving to go toward the oxygen. Now, this lowercase squiggly d I wrote just means a little bit. It's a fancy way of saying a little bit or partial. So these are not full charges. This is not a full -1 charge. It's a partial negative charge. This is not a full positive charge. It's a partial positive charge. This bond has two ends. It has a positive end and a negative end. And another way to say that is that it is a die for two, and pole. A pole is just another word for an end. For example, the North and South Pole are the two ends of the Earth. So that's what that is. As a noun, if you want to describe this bond with an adjective, you would say that that bond is polar. It has ends. It's endy. And so these polar bonds are places where you have partial negative and positive charge. You create them because of big differences in electronegativity. So I think a natural question would be, how do you know when you have big differences in electronegativity? And kind of as a rule of thumb, and this is really just a rule of thumb, so there will be exceptions to this, but it's an important rule of thumb, you'll have big differences in electronegativity either when you have really electronegative atoms or when you have really not electronegative atoms. Now in the top right of the periodic table, you will see, in the top right, Look at the top right, you'll see nitrogen, oxygen, fluorine, and chlorine. That top right part. So you have nitrogen, oxygen, nitrogen, oxygen, fluorine, and just below that is chlorine. Those are the most electronegative elements. You might say, why not the noble gases? Those noble gases at the far right already have all their electrons paired, so they tend not to react much. Of the atoms that react, nitrogen, oxygen, fluorine, and chlorine are really electronegative. So if you have nitrogen, oxygen, fluorine, or chlorine, those atoms tend to become slightly negative, and whatever they're bonded to becomes slightly positive. And we saw an example of that here. Oxygen, really electronegative, so it steals the electron density for itself, becomes slightly negative, and leaves what it's bonded to, the hydrogen, slightly positive. The other thing you want to watch out for are metals. Now, on the periodic table, a good periodic table will have a nice sort of zigzag line here, and the metals are going to be everything to the left of that line. In other words, the metals are on the left side of the periodic table. That means that they have low electronegativity, especially the ones all the way over here. So they have extremely low electronegativity, so the metals will tend to give their electrons away. They don't attract them very much, so the metals will tend to be slightly positive, and anything they're bonded to will be slightly negative. Okay, so I think now we're ready to dive in here. The whole point of doing this also is because the places where there are charges on a molecule is where that molecule is going to want to stick to or react with other molecules. So ultimately, we want to be able to take molecules we've never seen before in our life and know how they'll react. In organic chemistry, that's what we want to do. And the first step to that is being able to see these charges. So the first thing I'm looking for are nitrogen, oxygen, fluorine, or chlorine. Those are really electronegative atoms, and here I see one. It's going to take the electrons in these bonds and pull them to itself so that it becomes slightly negative. And if those electrons go toward that oxygen, the two atoms it's bonded to, the carbons, will be slightly positive. They're losing those electrons. I see another oxygen, and this falls in the category of nitrogen, oxygen, fluorine, or chlorine, really electronegative elements. This oxygen is going to really attract the electrons in these bonds and become slightly negative. If those electrons spend all their time around the oxygen, the carbons are going to lose them, and so they'll become slightly positive. And so you can see where this molecule has slight charges, positive and negative charges, based on those big differences in electronegativity. You would also want to check it for metals, but we don't have any metals here. And so all of these are on the right, all of these elements are on the right if you look at a periodic table of this zigzag line. Oops. Okay, how about this one? So first, look for nitrogen, oxygen, fluorine, or chlorine. I see a fluorine. That is really electronegative, so it's going to take the electrons in that bond, pull it toward them itself, and that becomes slightly negative. And if the electrons go toward the fluorine, the carbon will be slightly positive. Okay, again, look for nitrogen, oxygen, fluorine, or chlorine. I see a chlorine here. That chlorine is going to pull the electrons in this bond to itself and become slightly negative. And the atom it's bonded to, the carbon, will again become slightly positive. And so we see the slight or partial charges in this molecule based on those differences in electronegativity. You also want to look for any metals, because metals have really low electronegativity, so they'll lose their electrons, give them away to whatever they're bonded to, but we don't see any metals here. All right, so look at this molecule. You're looking for nitrogen, oxygen, fluorine, or chlorine. Now I don't see any of those. We do see bromine. Bromine is just underneath chlorine, so it's got a pretty respectable electronegativity. But the key thing here is the second thing that we always want to look for, metals. And we have a metal here, magnesium. If you notice, magnesium is to the far left of the periodic table. It's over here, number 12 in the top left, and you can see that it's definitely a metal. So magnesium it has very low electronegativity. It doesn't attract electrons very much. So that tends to lose its electrons. The electrons are much more attracted to whatever the magnesium is bonded to. So the electrons in these bonds go toward the other atom, attracted to that one more. The carbon and the bromine, become slightly negative, And the magnesium is losing its electrons, so it becomes slightly positive. How about this molecule? This is actually glycerol. It's the backbone for triglycerides, the fats, the way your body stores fats. So here, we want to look for the charges. We're looking for nitrogen, oxygen, fluorine, or chlorine, and I see oxygen in a few places. All of these oxygens are really electronegative. They're going to pull the electrons and bonds toward themselves and become slightly negative. And the atoms that they're bonded to will lose those electrons and become slightly positive. So all of these partial charges would be sprinkled around this molecule, and it's at those charges, those sticky places, that this molecule will tend to interact or react with the world around it and change. For this molecule, remember the procedure. Look for nitrogen, oxygen, fluorine, or chlorine. I see an oxygen. The oxygen is really electronegative. It's going to pull the electrons in these bonds toward itself and become slightly negative. If those electrons go toward the oxygen, then the other atom in the bond, the carbon, will lose them and become slightly positive. The second thing you want to always check for are metals. We don't have any metals in this molecule, and so this molecule is actually acetone, which you'd sometimes use as nail polish remover, and so that's where that molecule tends to react with other stuff at those two atoms. How about with this one? Here you're first look for nitrogen, oxygen, fluorines, or chlorines. We see chlorines everywhere. They're all pretty electronegative. They're going to steal the electrons in these bonds and leave that carbon really slightly positive in all of these bonds. So this carbon is really going to be pretty slightly positive. And we end up with those partial charges.